that we're given. The way this works is they give you an equation and they would say, which slope field is this? That's one way to do it. And then we'll actually do some graphing. So this one, the slope field, if you're seeing my screen, is sine x. So that's a little bit maybe different. We haven't seen that before. So I think one of the challenges would be like, well, I don't know, do any of these stand out to you from this one? Maybe we could talk about why it stands out.
Sine. Well, you could go off of like C because that kind of looks like the graph of sine.
Yeah, and the problem is though, is that this C is actually, what is the antiderivative of sine? Do you remember that?
Cosine.
Negative cosine of that. So like you, if you were to graph some of these solutions, let's see here, they obviously do oscillate. That's not great, but they kind of do oscillate. But you got to be careful. What if there was another graph of, like what if there was one that actually did look exactly like sine? That would be a problem here. So what I would suggest is still using that technique of like, well, what's going on at 0 here? When x equals 0, what is the sine of 0?
1.
0. And that's why all of these, that means that the slopes are 0 everywhere.
Oh, so wait.
So like one choice to solve this is to actually find the antiderivative.
Yeah.
And then you're just tracing to see if it looks like that. Now, I can do a little better job than I did here of tracing minus cosine. Minus cosine it actually starts here. It looks like that and goes the other way. That's minus cosine. So you can actually see it there, plus C in this graph.
But if you plug in 0, like sine 0, what do you mean slopes are 0? Like slopes are 0 are?
Yeah, that's what this if we're to just like translate it, the slope is sine x. That's what this means, this equation.
So how does that help you find the right one though?
Well, in this case, like this is the only one that had this sort of oscillating behavior, but at 0, it matches what we were looking for, which is that when you put 0 in for x, the slopes are 0 everywhere.
Oh, okay.
Yeah, but what I was suggesting is like they could give you one that looks like sine x or cosine x.
Couldn't B also work for that?
Let me try to let me go to Desmos here and snip in.
But isn't like at 0 for B, it's also 0? Like
yes. But let me try to do a better job of explaining this. But it doesn't have the oscillating behavior.
Right.
Why is this only in there? Okay. Well, that's not gonna be very fast, but that's one technique you can use here. Let's look at another question, and maybe it'll be more obvious what I'm trying to explain here. Like there's a few options to do this. Like the last option though is to actually try to calculate the slope at every point. You don't want to do that unless you have to. So the second one here is this equation. Let's go up to the right here. The dy dx, the slope everywhere is x minus y. Okay. So when x minus y equals 0, that's kind of your first thing you're looking for. Like you almost always set these equal to 0. We didn't do that in the last problem, but that's that's kind of a technique. So you can put 0 in, or you can set it equal to 0. You generally set it equal to 0 when you have two variables. So when x equals y, okay, the slope is always 0. Like, and if you need ordered pairs, like let's say x is 1 and y is 1, that leads to dy dx equals 0, because that 1 minus 1 is 0. 2, 2, same thing.
Yeah.
Any of those. So you're looking for somewhere where this line on the graph here has 0 slope. was that,
1, 2, 2, yeah.
those all have that slope there. And that's kind of what you're looking for when you something to kind of give away which one it must be.
Okay. That makes sense.
Let's do another one here. So like, again, a couple of techniques here. One is to just set it equal to 0. One is to figure out like what happens at like of 0. Okay. Now, when it only depends on one variable, like in the next problem here, grab this one in the next problem. When it only depends on one variable, you may have a different approach here. So since this only depends on y, you know this equals 0 when y equals 2. So the slopes.
So
of
you're looking
0.
for a slope of 2?
No. When y is 2, so y is 2 is this line right here in A.
Yeah.
The slopes are 0 there. They're horizontal.
Oh. Okay.
So, so that, I mean, that's why it's A. I mean, that's one way to do it. The last one. Oops, did that stop sharing?
Yeah.
Okay, sorry about that. Hit the wrong button.
Okay. There we go.
Yeah. So for the last one here, we're gonna make a slope field for it.
Okay.
We'll just do this one on our own rather than grabbing that. So we want to make a slope field for dy dx equals x, and we only need to do it at a few points here. So
x equals 0, right?
yes, but let me just like pretend like these are the grid points that we're gonna do it at. That's probably as far out as you would be asked to go, like a 3x3. Okay, so that's all there. All right. So when x equals 0, okay, which is along here, along the y-axis, what are the slopes there? What does that mean when it's a slope of 0?
Horizontal, yeah.
Horizontal. So these all have, let me do a different color here. They all have a horizontal line at 0. Now, the other one that's sometimes interesting is
vertical. What is the slope of a vertical line?
It would be undefined. So you're looking for like 1/0.
Oh, okay.
So another interesting point would be like, well, where is the slope? When does this equal 1? Well, in this case, it's when x equals 1. So along this line here, it has a slope of 1. So a slope of 1 looks like this.
Wait, so you just plugged in 1?
Yeah, because like along here, along this line, which is x equals 1, the slope is the x value. The slope is whatever the x value is.
Oh, so the next one is 2. So less steep, right?
Steeper, because up 2 over 1, like if you were to go up 2 over 1, it looks like this compared to this line right here.
Okay.
So I've overdone that. You definitely don't want to make it that big on the, you just want to, you want to show steeper. Okay.
So
how about up here at -1?
So that's left 1, wait, up, no, down 1 over 1. So then that's like, yeah.
-1.
And then down 2 over 1. So more steep.
Yeah. Well, yeah, this one is going the other way though. Like,
yeah, like
I don't know, it's negative steeper.
Yeah.
Okay, great. All right, so let's have you try one on your own here if you think you understand this. I'm going to just stop sharing for a moment. I'm going to go back to our previous lesson because I think they had some slope fields that were, I'm just going to grab that image of the grid.
Yeah.
To make this better. So let me go back, grab it. Okay, I found it. Okay, so let me share my screen and I'm going to ask you to graph dy dx equals y.
Okay.
So it's really similar to the previous one. We can look at this again. It's similar, but it's not the same. So take a minute or two, work your way through that, and then I'll show the solution here shortly.
Okay.
Any questions, or you can take more time, but just want to check in, see if there's any issues.
So is it the same thing where you just set it equal to 0?
Yes.
Okay, so at like the 0 points, is it just like vertical lines?
Well, this case, it's saying when y equals 0 is along the x-axis, and that's a
Oh, I see. That's the okay.
that's horizontal there.
Right. So that okay. So then if you do like so then you plug in 1.
Yeah, like I would set it equal to 1. So like hopefully you got these three there.
Yeah.
Okay, now where does it equal 1? It equals 1 when y equals 1.
So
Where is that? That's
okay.
here.
Yeah.
But what is the slope of y equals 1? What is the slope of 1 look like? And it's that up and to the right.
Oh.
So
So
now
then
I'm starting to understand. So like this tells you where, and then this tells you what. This is where, but the number itself tells you what it is.
so that y equals 2, it's like more steep.
Yes.
And then at y equals -1, it's like the same as the 1, but like negative.
Yeah. Yes.
Okay.
Yeah. Do you want to do more of these?
Maybe just like one more.
Okay. So you want to graph it.
Yeah.
All right. All right. So here is possible problem you might see. Dy dx equals 1 minus x.
Okay. Just gotta make the graph. Okay.
I'm just gonna just go ahead and work through it. If you have questions, let me know. I'll work
Okay.
it out with you in a minute or two.
So I set it equal to 0,
Yes.
and then you get x equals 1. So is that like when x is 0, they're all like slope of 1?
Yes. When that's the where, and then this is the what. So it's x equals 1 is where you're going to do that, which is over here on this side. And then what it is the slope is always 1 there. I'm sorry, slope is always 0. Sorry, I misspoke.
Oh, I had that backwards. Okay, so I did it wrong then. So okay, see x equals 1. So then how do you do the other ones?
So we want to know when 1 minus x equals 1, because this means a slope of 1. We know how to draw that. So you solve it. And when you solve it, you get x equals 0. So
How do
that's
you know,
where,
how do you know to set it equal to 1?
because that's a nice thing to, so when it's only in one variable, you generally set it equal to numbers.
Oh. So that's x equals 0. So then at 0, they're all slope of 1. Okay.
Yes.
And then you do like 2.
Well, it's kind of like, it depends on how much of your grid you got, but you want to set it equal to slopes that you know. Or like in this case, because you know that x really this is when x is 1, x is 0, and x is minus 1. That's kind of your options because it doesn't go out further.
So
But let's
you do
just,
-1.
yeah, and you might as well do x equals 2 to show kind of the full thing. But we're going a little too far ahead. So when x is 0, you have a slope of 1. That's along.
Yeah, I got that.
Okay, now let's do it when, let's do it now when x equals minus 1.
Okay, so negative x equals 1 minus 1 minus 1, so 2.
So where it is x equals minus 1, and then what it is the slope is 2. So it's steeper.
Okay, and then you could do 2.
Yeah, I think that would be reasonable to say, okay, x is 2. So that's where it is. And then 1 minus 2 is -1. That's what it is. The slope is -1 there.
Right, okay. All right.
Yeah. So like if like there's a couple of types of problems you might see. One is where it's just in x or just in y. So some examples would be like dy dx equals x, dy dx equals x or y plus 1. Like these are, and when they're just in one variable, you can either substitute for x or y, like we just did.
Okay.
But when they're in two variables, and so an example would be like x minus y.
Mm-hmm.
You have to set these equal to 0 to sort of look for a pattern in the slope field.
Well, the last one wasn't 2 variables, and we set it to 0 though.
Right. So you can use that approach for this one on the left here. But this one on the right, like what you don't do on the right is you don't substitute in like ordered pairs because it takes too long.
Gotcha.
Okay. You have to look for like a relationship, like when x equals y, it's 0, and when x is 2 more than y, it equals 1, so that you can like figure out where the nice slopes are. And so the nice slopes are the following: 0, 1, and -1. Those are the ones you're looking for.
Okay.
Another option also is to find antiderivatives. That's another technique that we talked about. Do you want to do any of those?
So you find the antiderivative and then what?
You have to then trace that curve on the slope field and see if it matches.
But I wouldn't probably know what the what it looks like. You know what I mean? Like,
Right. So like, let's say, let me just give you one example like that, and then we can move on. If I can find the slope field thing. Where did you go? There you are. Okay. So let's say this one doesn't help, very helpful. Yeah. Okay, never mind. I was trying to give you one that like you might see, but this tool isn't going to work for me for that. Okay, so we should move on to something else. You said some more like Newton's law of cooling or growth and decay.
or use substitution stuff. Whatever, honestly.
Okay.
And there's some on the PowerPoint for that I sent for, like I sent it a couple days ago, but I think it's attached to today's like.
Okay.
email.
Yeah. Let me. These all are way more complicated than that. Pan. This one.
On the PowerPoint.
No. Just I'm trying to find some other ones. So, okay. Let me go back to your PowerPoint. This is for 7. This is just the review.
Yeah.
Okay. Yeah, I mean, I'm only seeing that one the aluminum beam problem.
So are we doing those or the use substitution?
Oh, do you want, we can do both, but use substitution problems is what you like to do next.
Sure.
Okay, either. All right, let me look for some. These are hard to make. Okay, here we go. Okay, so first problem here, use substitution problem.
So the u is 3x cubed plus 2.
Yes, and then you have to immediately take a derivative of that. So that's 9x squared dx, and then you solve for dx.
Okay, so you do integral 45x squared over u to the 4th dx. Oh wait, how do you do? Okay, so you solve. So you just divided the 9x. Okay.
Exactly. Yeah.
Du over 9x squared. Okay. So u over 9. So then you cross cancel, like.
Right. So you get integral 5 over u to the 4th du.
Yep.
Okay. And then you can bring the 5 out if you want, but this equals u to the minus 4th du. So it's a power rule integral.
Doesn't the du and the integral cancel at that point?
Not until you've dealt with it. This is just a rewrite step. There's no calculus here.
Oh.
You're just
What do you mean dealt with it though?
When you apply the power rule, that's when the du goes away. The du is always there when you have this symbol, this integral symbol.
So power, like, are we like antiderivative here?
Yes. When you take the antiderivative of this, when you write that next line, then the integral and du goes away.
Do I have to do the antiderivative to the 5 too?
It's multiplying, so it just comes along. It's just a constant.
Okay, 5u to the negative 3 over 3
plus c, very important.
Plus c, yep. And then you put the u back in.
Yes, you always back substitute.
So 5 times 3x cubed plus 2 to the negative 3 over 3 plus c. Do you just do that?
That looks good. This
Wait,
one
does it have to be 5?
It doesn't really matter where you put the negative. I mean, my preference is in the numerator, but that they're just testing. Do you understand
Can
how
you put
to?
that whole thing, can you like 3x cubed, all that on the numerator and then put the negative 3
Yes.
on top? Okay.
Yeah. Yes, that's okay.
All right.
All right, so let's do another one here. This one is an E problem.
Oh, it's hard to find the, so is the u the 5x squared?
Yes, it's exponents. It could be things in parentheses. Could be
Oh
things under
yeah, can we
roots.
do next one of the like ones with like cosine or sine? Because I'm
Yes,
confused by those. Okay.
yes,
So then it's 10x dx, and then the dx is du over 10x.
yeah. Du is 10x dx.
And then it's integral negative 50.
X e to the
X,
u.
u, and then du over 10x. So then the 10x, 50x. So that becomes 5. So it's negative 5 e to the u du.
Mhm.
Should you move the negative 5 to like the front of the integral? Yeah.
Probably for you, you should. That's a
E to the u du, and then
it's the antiderivative of the u is e to the u, like you said, and then you gotta substitute in that u. So your u was 5x squared plus 3.
e to the 5x squared plus 3 plus c, and then do you leave it like that or should you do like
Yes.
ln?
No,
Okay.
no, you're not. There's no equal sign. You're thinking of initial value problems. No, this is it.
Okay.
Okay, so you asked, this is very important. Let's go integral from 0 to pi over 4 sine x cosine x dx.
Integral pi over 4 0. Okay, so
So just at this point, just pick one. I'll pick for you.
what if it's like negative cosine? It couldn't be like a negative of those?
It could, but let's just do this. Let's just make u sine x. So du is
Negative cosine.
cosine x, not negative because it's derivative.
Wait, is the antiderivative negative cosine?
Yeah, so you gotta go this way. So if you always start with sine, the derivative of sine is cosine. The second derivative is minus sine. The third derivative is minus cosine, and then you get back to sine. So it's like
Okay.
you have to know this progression really well. Be really comfortable with it, and then the antiderivatives work similarly, but like I would just pattern this like sine, derivative of sine is cosine, so antiderivative of cosine is sine, and then the antiderivative of sine is minus cosine because this negative would come with it. But for now, like just you got to be comfortable going forwards and backwards. So just maybe take a moment when you're in your own study time to really look at this again. If you got it. Okay, so du is cosine x dx. So dx is du
Over cosine x.
right. So this
I
is the
just
end.
don't get how you choose between the sine and the cosine.
Well, we'll do it the other way, and you'll find it actually doesn't matter in this problem.
But like,
But
what if it does matter?
well, I mean, you're kind of in this introductory part of the course, so you would hopefully have enough time that if you chose the wrong one, you could go choose the other one.
But would it be a case where it's like if you're given sine and cosine, it's like it's a negative of one of those as your u?
No, your u is always whatever's here. Like you're not making
Oh,
anything weird.
okay. So it's u cosine x du over cosine x. Your cosines cancel. So then it's integral u du.
Right.
And then you do, is it like u squared? Yeah.
Yep.
Okay. So u squared over 2. And then that's sine x squared over 2 at pi over 4 and 0. So then sine pi over 4 is root 2 over 2 squared. So that's root 2 squared.
Yeah, root 2 squared is 2. Bottom is
Because it's
4.
root 4, 2. Yep. So
Yep.
1 and then minus 0. So it's just 1.
1/4.
Wait, 1/4.
So the inside is 2 over 4 times 1/2.
Oh, I forgot to square the bottom.
That'll do it. Okay, so
Wait, so 2 over 4. So that's 1/2.
well you're multiplying.
Where's the other 1/2? Because isn't it sine x squared over 2?
Well, it is. So the way, okay, so let me write it the way you're writing it, and then this will make more sense. So you're doing sine. I'm sorry. So you're doing the square root of 2 over 2 squared all over 2.
Oh, wait, I see. I forgot the other 2 over 2. So then that's times 1/2. Okay, gotcha. So that's 1/4.
Okay, so let's go back and do this problem now with the other substitution, and just follow along here because I don't want to take a lot. I want to get another couple examples like this. But so let's say u is cosine x this time.
Okay.
Du is minus sine x dx. So it becomes the integral sine x times u, and then du over minus sine x. So then you get the integral of negative u du.
Mm-hmm.
And then you get negative 1/2 u squared plus c. So it's negative 1/2 cosine squared x, evaluated from 0 to pi over 4.
Oh.
Okay.
So before.
So, well, let's make sure. So this is cosine squared pi over 4 minus a minus 1/2 cosine squared of 0. Okay, so on the left here, it's the square root of 2 over 2 squared times negative 1/2 plus 1/2 cosine squared is 1 squared if you want. So this becomes 1. This becomes 2 over 4 times negative 1/2. So it becomes negative 1/4 plus 1/2, which still equals 1/4.
Oh, okay.
So remember I said it doesn't matter. That's why it doesn't matter, because you get the same answer. Now I do want to do this problem where it does matter which one you choose with you, because this one does matter. Like you have to do this one correctly. So forget about this on the right here. Just imagine you're given this.
Okay. So should I just choose one and then try it, or?
Well, you want to choose the one that's to the power. So u is cosine x. Well, no, but maybe if you were to see this on your exam, you would want to choose, like, let's say it was sine cubed cosine x, you would want to make it the one that's to the power. So sine.
And it wouldn't ever be like cosine. Wouldn't you include the power in your u?
No, you would not do that.
Okay. So cosine, so that's negative sign.
Yes.
Okay.
So it's integral u cubed.
X dx, and then wait, the dx is du over negative sine x.
Yes.
So then integral u cubed sine x sine x. So then those cancel. So then it's integral u cubed du. So then it's negative u to the fourth over 4. And then you bring back, so cosine x to the fourth over 4 negative plus c.
Yes.
Yep. Oh, and then are there limits or not for this one? Or like numbers?
No, I didn't put a name for this one. Okay. Okay. Let me throw one at you here that hopefully is okay. X over 1 minus x dx.
The
What do you
1
think?
minus x.
Okay, so let's go through that. So then du is minus dx. So you get the
Because we're just
integral.
doing, wait, because this derivative of x is just 1,
Yeah,
right?
yeah, there's a negative in front.
Okay.
So it's over u.
Dx, so then dx is, wait, dx would be d just negative du.
Yes, yeah, or du over negative 1. Do you see a problem with this?
Yeah, you can't cancel.
Yeah, so, but this is actually correct. So this is one of those like exception problems that I'm only showing you, like hopefully you since you saw it once, it'll help. You end up solving this line, you solve it for x.
Oh, that's odd. Okay.
It is, but it's totally reasonable for your instructor to ask this, and it throws most students off.
Wait, so you solve it for, okay, so you move the 1 over negative x equals u minus 1, and then divide, so x equals negative u plus 1.
Yeah, or 1 minus u, but I'll use I'll go with minus u plus 1. So now that goes up here, and you will see now how this actually worked. You know, maybe it won't at first glance, but
Minus u plus 1 over u. So then your u's cancel.
well, you got to divide both of them. But let's deal with this negative first. So let's negate both of these top ones. So it becomes u minus 1 over u du.
Okay.
That's all we did there. So now you can divide both of these by u. So it's integral u over u minus 1 over u du. So it's integral 1.
Oh, wait, so now you just put your, wait, what did you do there?
You
just put your-
divide both of these by u.
Oh, okay. 1 over u. Okay.
So now you can actually do this one.
So x, wait.
The antiderivative. Yeah,
right?
that's the antiderivative.
Wouldn't it be x, not u?
We're not, we're going to back substitute u at some point, but not yet.
Wait, but in all our other ones, we put in.
Not until we found the antiderivative.
Okay, I see.
You find the antiderivative, then you put that back.
U plus c, and then you have to, oh, then you put the u. Okay, so 1 minus x minus ln 1 minus x plus c. And that's it.
That's
right?
it. Yeah.
Okay.
Okay. So let's do another one kind of like this, like, because you may see it on the exam. It's different than what we've done before. So the key here is when you put all your stuff back in, the x doesn't cancel. And that means you either made a mistake or there's like another little step to think about.
Right, okay.
Okay, so we'll do something, it's gonna be really similar. Integral x over square root 1 minus x. Or let's do x plus 1 this time.
X over
X plus 1 dx. So u equals
X plus 1.
x plus 1. So
So then
du equals,
just dx, and then your dx is,
so this is x over the square root of u du.
what is, how do you solve for, don't, wait, what, dx is equal to d, oh, wait, I see.
Yeah.
Okay. So x over, okay.
But there's still an x. You know, that's
So
the,
you do x plus 1 equals 0.
no, you solve this one, you solve for x.
Oh wait, I forgot that there's u. Okay. So x equals u minus 1.
Yes.
And then you plug that back in.
So
So x, no, wait.
So you've not made it better quite yet, but it's getting better. It's really close.
U. So then it's u over root u.
Right, but let's write it as
1 over root u.
u1/2 minus 1 over u to the 1/2 du.
Oh, okay.
Because we're gonna use the exponent rules here.
So you do antiderivative? Yeah.
Not yet.
What? Oh.
Well, you want to use your exponent rules, like you want to reduce it. That's the whole reason you're doing this.
Wait, so you just did 1 minus 1/2, right?
Yes. So whenever this integral symbol is there, you still haven't done the integral. You're still just evaluating the thing.
How do you do the, so there's no exponent. Oh, it's 1, I guess, right?
Yeah. Well, this is the left one is 1 minus 1/2. On the right here, it's just that you bring it up and make it negative.
Wait, what? Say that again?
We're using this property, x to the n over x to the m, x to the n minus m. That's the first
How do you
one.
do it for the 1 minus?
1 over x to the n always equals x to the negative n. You just bring it up in the numerator, but it's negative.
Okay, so then you put in your u, right?
Now you're ready to find an antiderivative.
Oh, wait, okay, so you
like up until this point, you don't know how to do this. Like none of these lines work out nicely. So like that's why this process is carried on until you're like, oh yeah, I know how to do that one.
u to the 3/2 over 2/3.
It's over 3/2, but it becomes 2/3, like you said. It becomes 2/3 u to the 3/2, but it's over 3/2.
2/3 minus 2u.
Yes.
1/2.
And u was x plus 1.
2/3 x plus 1, 3/2 minus 2, x plus 1 to 1/2 plus c. And you just leave it like that.
Yeah.
Okay. Can we just do one of the Newton things before? Done.
Sure. I couldn't find one that was nice. So can I just make one up from that? Just change the numbers from the one that was given. Do you know if you're gonna be allowed to use your calculator on that part?
Well, there'll be like a calculator and non-calculator section. I don't know if it'll.
Okay. I mean, this one's probably a calculator, but the way your instructor did this is that it wasn't. So let's say aluminum beam was wrought on the outside where temperature is held at let's say it's a little nicer. Let's go with 70 degrees inside, and let's do after 20 minutes it warmed to 40 degrees. And after 40 minutes, it warmed to, let's go 65 degrees.
Okay, so it's T, so that's your starting.
I think that's, let me see here. Where did you, there it is. Equals T0 minus TS e to the minus KT. Oops, let me go up.
So your TS is T minus.
Your TS is 70.
E to the negative. Okay.
The other two points are just, they're just data points. They're little t comma big T is the ordered pair. So it's like after 20 minutes is 40 degrees. After 40 minutes, it was 65 degrees.
So you substitute those in right now?
Yeah, you have to do them one for
So-
each equation. So
So it's like 40 minus 70 equals T0 minus 70 E negative 20K. And the other one is 65 minus 70 T0 minus 70 E to the negative 40K. Okay.
yeah. So
And then you
what
divide them, right?
you divide, and the nice thing is that these first things cancel out. And
Right.
then on the left here, it's minus 25 over minus 5 equals, I'm sorry, minus 30 over minus 5 equals, and then it's minus 20K minus 40K. It's that X to the n over X to the n. We subtract them.
Minus 20 plus 40, so 20.
Yeah.
Okay, and then that's 6 on the left equals e to the 20K. You do ln of, ln 6 equals 20K, and then K equals ln 6 over 20.
Right, and then you go back to one line or the other. I'm going to go back to this line.
Right.
And you plug it in here. So your
Doesn't
K,
matter which one though.
it doesn't matter which one. This one divides by 20, so it's slightly nicer, I guess. It's 40 minus 70 equals T0 minus 70 e to the minus natural log of 6 times 20 over 20. So 20s cancel. This negative actually comes up here as an exponent.
Okay.
So you end up getting e to the natural log of 6 to the minus 1 power, which is really 1/6. This over here on the left is minus 30 equals T0 minus 70 times a 6th. So you multiply by a 6th. I may not have chosen reasonable numbers on here. So you multiply by 6 on both sides. So you get negative 180 equals T0 minus 70. Add 70 to both sides. So the beam was a negative 110 degrees to start.
Okay.
We do unfortunately have to stop here. I'll send you the notes here shortly.
Okay.
And I'll see you next time.
Thank you.
Welcome. Bye now.
Bye.